Any vapor compression system has four components, or you may also refer it as four stages. I will refer them as four components. And those four components, whether you're using the different types of heat pumps that we will mention as we go along, they all have these components. And those components are, we've got the evaporator, we've got the compressor, we've got the condenser, and we've got the expansion valve. Okay, so the four components of any vapor compression system are the evaporator, compressor, condenser, and expansion valve. So these are the four components, or you may also refer them as maybe 4 stages. So if I divide the system into half, like this, so let's start, I'll number them as 1, 2, 3, and 4. So we'll know the different points across the circuit. So I will start with the primary function of an evaporator. Okay, so an evaporator takes, again, depending on the source, let's start with air in here. So it takes air, and of course, inside the 4 components, we have a refrigerant, which constantly changing its phase from liquid to gas, gas to liquid. So inside the evaporator, so at point number 4, what we start with is a low temperature and low pressure liquid, and that is what's going into the evaporator. And of course, as it travels through the heat exchanger or the evaporator, the refrigerant boils. Okay. The benefit or the advantage of using a refrigerant is it boils at a very, very low temperature. For instance, if we're taking, let's say, R134A as an example, as a refrigerant, and that refrigerant boils at minus 16 degrees C. So as you can see, it boils at a very, very low temperature. So that low temperature and low pressure liquid gets boiled, and when it comes out at point 1, we have low temperature and low pressure vapor. Okay, so at this point, at point 1, we have a low temperature and low pressure vapor. And then we feed it into the compressor. Okay, and the primary function of any compressor is at this point, or point 1, we have vapor. But that vapor is a very, very low temperature and low pressure. And the benefit of a vapor or a gas, by reducing its volume or by compressing it, we are able to change its property. So what we do is we use the compressor, we compress or reduce the volume of that low temperature and low pressure vapor, and therefore when it comes out here, it comes out at high temperature and high pressure vapor. Okay, and that is actually what we use for our application. So imagine here you have high temperature and high pressure vapor that you can use it for different applications, whether for space heating or whether for hot water, depending on the application again. But the only way to extract that high temperature and high pressure is to pass it through a condenser. And by passing it through the condenser, what you're doing is actually you're sinking those high temperature and high pressure. So here you will have a secondary circuit to remove the heat from the condenser. And again, we will look at it, whether you're using air to remove the heat from the condenser or whether you're using water to remove the condenser. And that's how actually a condenser is classified, based on either air-cooled or water-cooled condenser. So at this point, we have high temperature and high pressure, and we pass it through a condenser. So as it passes through the heat exchanger, condensation occurs. a condensation. At the end, we have, at point 3, we have high temperature and high pressure liquid, okay, with some droplets or some vapor, very, very small amount. The remaining, of course, using the condenser, you're rejecting it into either air or water. So therefore, you're removing the heat from the condenser. And therefore, at point 3, we have high temperature and high pressure liquid. And remember, at point 4, we had low temperature and low pressure. And in order to reduce the temperature of the liquid from high temperature to high pressure, what we do is we pass it through an expansion valve. Okay? How do we reduce the high temperature and high pressure to low temperature and low pressure? It uses Bernoulli's principles. There is a venturi inside the expansion valve. So by suddenly reducing the area of the pipe, you are able to expand the liquid. Therefore, you're able to reduce the temperature and the pressure. So this is a Bernoulli's principles that says if you reduce the area, you also reduce the pressure. You increase the velocity, but you reduce the pressure. And if you reduce the pressure, therefore you also reduce the temperature. So therefore, as you can see from point 3, when you come back to point 4, you come back to the same point that we started, which is low temperature and low pressure liquid. And then, of course, you feed it back again to the evaporator, and the circuit repeats itself. So at the beginning, as I said, if you divide the circuit into two halves, as you can see, anything below the line, it is low temperature and low pressure, and anything above the line, it is high temperature and high pressure. Okay, so you can divide the circuit into two. Anything below the line, we have low temperature and low pressure, and anything above the line, we have high temperature and high pressure. That is the basic principle of any vapor compression system. Using those 4 components, you're able to boil and evaporate the low temperature and low pressure inside the evaporator, and then you feed it into the compressor. By reducing its volume, we're able to increase the temperature and pressure of the vapor. Therefore, we have high temperature and high pressure. And then by passing it through another heat exchanger, which is the condenser, by going through the process of condensation, we are able to change it to liquid, but at high temperature and high pressure liquid. And then by passing that high temperature and high pressure liquid through another expansion valve, and by using Bernoulli's principles, we are able to reduce the temperature and pressure. And at this point, of course, I want to iterate the importance of pressure and temperature and the relationship between the pressure and temperature. If you increase the pressure, you increase the temperature. If you reduce the pressure, you also reduce the pressure. So pressure is important in refrigeration systems. And we will look at them as we go along, how evaporating and condensing pressures also affects the performance of any system. And by monitoring and controlling the pressure of systems, you can play around with the performance of the system. So that's generally how a vapor compression system operates. I'm going to quickly go through some basic terms that you will come across in the refrigeration industry generally, like sensible heat and a latent heat. They both deal with either heat extraction or heat added into material or into any aspects, but one results in the temperature change, only temperature change, and the other one results in state change. Okay, so the sensible heat results in temperature change, as opposed to the latent heat, which results in state change. And a good example of latent heat is ice melting. Some terminologies that we would be using are saturation temperature. This refers to the transition of, so if you boil a water, for instance, the point at which water starts to boil, that transition point, that's where we're referring by saturation temperature. Okay? And we will use terms like evaporation temperature or condensing temperature. We are actually referring to the saturation temperatures. So we will use some of these terminology so you would know what we are referring. So water boils at 100 degrees C, but because the boiling point of water can vary depending on the pressure. Pressure and temperature are directly proportional to each other. And for instance, if you take a water and try to boil it at, let's say, 4,800 meters at a pressure of 0.56 bar, the water boils at 83 degrees C. So as you can see, not 100, the one that we always say, depending on the pressure, water can also boil at 83 degrees C. So what I wanted to highlight here is the relationship between pressure and temperature. And that is critical in any refrigeration systems that we will look at. This is another graph which shows the saturation temperature and the pressure for a different refrigerants. So any refrigerant would have a saturation temperature, and the pressure also relates to that specific saturation temperature. Other terms that we will come across or we use is the superheated vapor. And the superheated vapor is referring to the temperature above the saturation temperature. And we can actually calculate our degree of superheat based on, so degree of superheat is equal to actual temperature minus Tsat. One example that I just gave you here is we have a water boiling. Of course, the steam is at 100 degrees C and the superheated steam temperature is 120 degrees C. What is the saturation temperature and what is the degree of superheat? TA is 120 degrees C, and therefore degree of superheat is 120 minus 100, which is 20 degrees C. So superheat, again, we will use it when we define our pH chart, what a superheat region, where our superheat region lies. And the next one, similar to the superheat, is the subcooling. Again, this is the other opposite end of boiling, which is the cooling. So this is referring to a liquid at any temperature below its saturation temperature. And we can calculate the degree of subcooling. Degree of subcooling is the Tsat minus T actual. Other terms that we will use is enthalpy and entropy. One deals with the heat content of the fluid, and the other one deals with efficiency of a process. The entropy tends to be a complex property,